So, we all know that AC power is usually characterized by a sine wave, but where do we get this waveform from? Well, if we focus on a single electron oscillating back and forth as it would be in an AC circuit, and plot its movement with respect to time, we begin to see our sine wave being created. Now, this sine wave is incredibly important as simply looking at this waveform provides a significant amount of information on the nature of the current or voltage being provided. Firstly, we will look at the equation of an AC sine wave, which typically comes in the form V is equal to D plus A sine omega t plus theta, where D is the DC offset or vertical change, A is the amplitude or peak voltage, omega is 2 pi f, where f is frequency, and theta is our phase shift or horizontal displacement. Now, we will look at how changing these values affect the shape of the waveform. So first, we can see that changing the value of A does what you expect and alters the amplitude of the waveform, increasing or decreasing the peak voltage. Next, we look at frequency. Now, these are not exactly to scale, but it shows the concept well. If we assume that our initial wave here on the left is our waveform at 60 Hz, the orange waveform above is what the waveform would look like at about 300 Hz, which is 5 times the initial, and the bottom one being 30 Hz or half the initial frequency. Next, we look at changing D, or the DC offset, which is simply the same as adding a flat DC voltage to the system. As we can see, adding 2 volts simply shifts the waveform up by 2 volts. And conversely, minusing 4 volts does the same, except it moves the waveform down 4 volts. Finally, we take a look at what changing the phase shift theta does. This can be described in either degrees or radians. As we can see, adding 90 degrees simply moves the waveform to the left 90 degrees, and again, minusing pi on 5 radians moves the waveform to the right pi on 5 radians. So as a quick note, finding the difference in phase between two waveforms is a common question and can be found using the following formula, where t0 is the distance between two common points on the waveforms, t is the period, and you can multiply this by 360 degrees or by 2 pi radians to find your angle in degrees or radians respectively. Another common question that usually follows the previous one is to determine whether a waveform is leading or lagging another. This can be found by determining the angle between two corresponding points on both waveforms and recognizing which one comes first respective of the other. Here we see that the yellow leads the blue by x degrees, or conversely, the blue lags the yellow by x degrees. Now, as we mentioned before, these waveforms are quite useful on their own, as by simply looking at them we can extract a number of pieces of different information, such as the voltage peak to peak, the voltage peak, the period, or the instantaneous voltage. Even more information can be extracted from the graph using simple calculations. For example, the RMS voltage, which is the equivalent DC voltage of the AC waveform, can be found by multiplying the peak by 0.707 or 1 on root 2. The frequency can also be found using the formula 1 on the period, and the phase shift can be read off the graph if there is any. That concludes this brief summary of AC sine waves. Thank you very much for watching.